All right, welcome back, everyone. So now we've moved on from simply dealing with certain consequences of time dilation and the Lorentz contraction. Now we get to deal with putting everything together into what's called the Lorentz transformation. So let's see how this works. The statement reads, 𝘭𝘭𝘰𝘥𝘶𝘤𝘵𝘪𝘤𝘮 cried out in pain at precisely the instant her twin brother 500 kilometers away hit his thumb with a hammer. A skeptical scientist observed both events, the brother's accident and Sophia's cry, but from an airplane traveling at 12/13 c to the right. Which event occurred first according to the scientist? How much earlier was it in seconds? All right. So let's put everything together that we know about the special relativity consequences. Again, we are contracting the direction that is perpendicular or parallel to the motion, so our perpendicular equations 2 and 3 are unchanged. Here, we write that the length is the position initially minus the v times time. Okay, so again, all the units are the same, and we're contracted by a factor of gamma. Cool, we like that. Where this is the original velocity, and then the bar, of course, sticks with the moving object, so we like that. Next, what we see is that the time also gets dilated, so we have to put everything with our original kinematics into the time units, and we still get that c squared term there. So we're looking good now, and let's see how this applies. All right, so of course, we like a good diagram. Let's note here on the diagram that our plane is traveling to the right at 12/13 c, so a large fraction of the speed of light. I'd hate to be on that plane. And we see that the brother and the sister are 500 kilometers apart. Not too far distance when we're traveling at that speed. So let's break it down even more. Our solution then is that we first need to define our frames. It makes absolutely no sense to jump into these things without having a proper frame defined. So with that, let the brothers' accidents occur at the origin, or time equals 0, in both frames. Okay. So in system S, all right, we see that the coordinates of Sophie's cry are at x equal 5 times 10 to the 5 meters, since we're 500 kilometers away, and that was at time equals 0. Now, in the S bar system, or the scientist system, again, the scientist is moving on the plane, so that gets the bar system. We have that t bar is equal to gamma with parentheses t minus v over c squared x, so we can plug everything in for that. At t equals 0, we see we're just left with these factors. And since this is negative, Sophia's cry occurred before the accident, according to the scientist. Now, this again is an S bar. What we need to do now is find what the Lorentz factor is. So as you see, we just plug in everything we need to for gamma. And we see that we end up with a 13/5. So t bar is equal to 13/5. And then we have a factor of 13 canceling and a factor of 5 canceling with the distance here. The c's cancel, of course, so we're left with a negative 12 times 5 to the 10 due to the 12 from the velocity carrying over. And then we have one factor of c left over, so that goes in the denominator. And we see that we happened at 4 times 10 to the negative 3 seconds earlier. So I think this is really cool at making us think about how we have to determine the frames and what to put in each particular frame. This to me is the hard part, of course, and we have to be very delicate with these definitions, but otherwise a fairly square and easy problem.